All right, let's set the scene. Imagine the perfect digital crime. An attacker slips into a network, grabs exactly what they came for, and then they're just gone. Poof. No witnesses, no fingerprints, nothing. All that's left is this feeling that something's not right. So how in the world do you solve a crime like that? How do you catch a ghost?
This is the exact problem that digital forensic investigators face every single day. The bad guys have a massive head start, right? And the crime scene, it's not a room, it's this incredibly complex web of servers and data. But here's the thing, even the sneakiest intruder leaves behind a trail. These tiny little digital breadcrumbs, echoes of their actions, just frozen in time. The real trick is knowing how to find them and how to piece them all together.
And that's where our number one tool comes into play: timeline analysis. Now, this isn't about finding one single smoking gun. It's more like, well, it's like forensics for time itself. We're going to take thousands, sometimes millions, of seemingly random digital events. A file getting created here, a login over there, a system setting changing, and weave them all into one single coherent story of the attack, from the very beginning to the very end. Every single investigation has to start somewhere. It starts with that one piece of the puzzle that just doesn't fit, that one thing that looks wrong. In the digital world, that means finding a file or a process that's just not playing by the rules. It's the very first thread you pull that can unravel the entire attack. So investigators get really good at spotting these things, these anomalies, by looking for files that just plain don't belong. I mean, think about it. Most legitimate software you use, it's digitally signed by a company you trust, like Microsoft or Google. But malware? Yeah, that's almost always unsigned. And then there's this really cool concept called entropy. A normal file, like a document, is kind of predictable, it's readable. That's low entropy. But malware is often scrambled, encrypted to hide what it's doing, so its data looks like complete random noise. That's high entropy. It's a massive red flag. It's like seeing someone wearing a parka on the beach in July. It just doesn't fit the scene. And besides those giveaways, there are other huge red flags. I mean, the really advanced malware, it tries to be a ghost. It runs completely in the computer's memory to avoid being seen by antivirus software. But the real tell, the thing that gives it away, is what the file is built to do. Investigators will actually tear it apart to see its capabilities. For instance, can it perform credential dumping, which, by the way, is just a fancy term for stealing all the saved passwords on a computer? Or is it trying to call home to a hacker's command server? If the answer is yes, well, you've definitely found your first big clue. Okay, so finding one suspicious file, that's a fantastic start, but it's almost never the whole story. An attacker hardly ever uses just one tool. To really see the big picture, investigators have to zoom out. They have to connect that first clue to everything else that was happening on that system at that exact same time. And the way they do this is by building something called a super timeline. Seriously, you should picture a detective's case board from a movie, with all the photos and strings connecting everything. That's what this is. It's one giant chronological master list of every single event from every possible source. Every file created, modified, or even looked at. Every change to the system's registry. Every single log entry. This is where the chaos starts to look like a story. Now, building one of these isn't magic, not at all. It's actually a really methodical process. First, you just collect everything, all those digital artifacts. Step 2, and this part is absolutely crucial, you have to normalize the timestamps. See, different parts of a computer can have clocks that are slightly off, or even be in different time zones. You have to get them all synchronized, all speaking the same language of time. And then finally, you use some really powerful tools to weave these millions of data points into that one single searchable story of the system. So now we have our super timeline. And with this, we can do something really powerful. We can finally see if the attacker was happy with just compromising one machine, or if they used it as a launchpad to jump to other, more valuable systems on the network. We call this lateral movement. And to track that movement, investigators are hunting for one thing: a pivot point. A pivot point is that aha moment. It's the breakthrough in the case. It's that one single entry in our massive timeline that connects the dots, the one that links the suspicious activity on one computer to a brand new suspicious event on a totally different computer. This is the clue that just blows the case wide open. Let's just walk through a classic example. So on our timeline, we see the attacker's first moves on what we'll call host A. At 8:10, a malicious file is created. At 8:15 is executed. Just a few minutes later, at 8:20, it sets up shop to make sure it can survive a reboot. Standard stuff. But then, look at 8:30 a.m. That's our pivot point. A new piece of malware suddenly appears on a completely different machine, host B. That's the proof. The attacker used host A to jump over to that file server. We've just caught them moving laterally.
And once you find that pivot point, everything else just starts to click into place. It's like the rest of the dominoes just start to fall. We can now take all of our clues, that first weird file, the persistence, the lateral movement, and arrange them in perfect chronological order to tell the complete, unabridged story of the attack.
And there it is, the whole story, laid out step by step. At 8:10, the initial compromise. By 8:20, the malware has dug in. At 8:30, we see that critical jump to the file server. But wait, they're not done. At 8:50, they escalate their privileges back on the first machine, giving themselves more power. And then finally, at 8:55, they achieve their goal on that second machine. From start to finish, every single move is now crystal clear, all thanks to the timeline. Now, it's really important to remember this. A timeline isn't absolute, undeniable truth. A really clever attacker can sometimes mess with timestamps to try and throw investigators off their trail. But even with those limitations, the timeline is, without a doubt, the most powerful map we have. It's our guide for navigating the absolute chaos of a cyber attack and turning it into a story we can actually understand and act on.
It really makes you think, doesn't it? Every single thing you do on a computer, every click, every login, every file you save, it all leaves a timestamp. It's like this constant, silent record of our digital lives, being written second by second. For an investigator, that record is a treasure map. And for the rest of us, well, it's a pretty powerful reminder that in the digital world, nothing ever truly disappears.